All right, welcome back. In this video, we're going to review for the Unit 4 test. And so we're going to be looking over some problems that I have gotten lots of questions about. So let's take a look. All right, so I'll start with number 20 from homework 4. I'll probably use this review video in future semesters, so this might not be question 20 in the future, or I could have possibly removed it. But anyway, in the current semester, it is question 20. All right, so it says the following table shows how one professor might grade on a curve. What percentage of students receive a grade of A? So in the table, students get a grade of A if they score greater than the mean plus 19/10 of a standard deviation. A B if they score between the mean plus 1/9 of a standard deviation to the mean plus 19/10 of a standard deviation, and so forth and so on for C, D, and F. The one we're interested in is A's. So this is a standardized way of grading. So this is not 90, 80, 70, 60 sort of grading, your typical grading scale. This is standardized grading. And so standardized grading is what's used for standardized tests. So back in high school, middle school, elementary school, you probably took lots of standardized tests. Generally on those tests, your grade, the percentage that you get correct, is actually not what's important. What's important is how many standard deviations away from the mean you were. And that's the same for the SAT and the ACT tests as well. They're all standardized tests. So anyway, so the point of that is that on this one, it doesn't matter what your mean and standard deviation are. You can choose anything at all. An A is anyone who scores 19/10 of a standard deviation above the mean. So I'm just going to make up a mean and a standard deviation. Let's say our mean is 100 and our standard deviation is 10. Okay, so we're looking for anyone who scores greater than the mean plus 19/10 of a standard deviation. So now we just plug those values in. The mean is 100 plus 19/10 of a standard deviation times the standard deviation, which is 10. And so that's going to give us 100 plus 19, since 19/10 times 10 is 19, which is 119. So basically, if in this teacher's class, the mean is 100 and the standard deviation is 10, then the teacher is going to give an A to anyone who scores 119 or higher. And so if you remember, this is a normal distribution problem 1. With the normal distribution problems, we have two different calculator functions we use, the normal CDF and the inverse norm. If we have a score and we're looking for a percentage, which is what we're doing here, then we will use the normal CDF function. So normal CDF. In this case, our lower, we're wanting greater than this thing, the mean plus 19/10 of a standard deviation. So 119 is our lower. Our upper is infinity, so 1e99 is what we'll use, which again is not infinity, but it's a big enough number that it will give us a close enough answer to what we're looking for. And then the mean, I put that as 100, and our standard deviation, I put that as 10. Okay, and that'll give us the right answer. And you could have chosen any other values for your mean and standard deviation. You could have chosen 0 and 1, or you could have chosen 17 and 3. It really doesn't matter. You can make up literally any value you want for the mean and standard deviation. And it's the exact same thing, because 19/10 is a z-score. That is the number of standard deviations away from the mean. And so it has the same area to the right no matter what the mean and standard deviation are. All right, let's jump to the next one. All right, so this one is a binomial distribution question. As a reminder, the way we can tell if something is a normal distribution or a binomial distribution is what the thing we're looking at is what the data type is probably a better way of saying that. And so in the past question, we were looking at scores, and scores are normally distributed because scores are continuous. They can be fractional, they can be decimal, they are any number. Whereas the binomial distribution are counts. So normal distribution is measurements, continuous measurements. So there are things we need a measurement instrument for. A test is a type of measurement instrument. A ruler, a scale, a stopwatch, a thermometer, anything that we need to measure something that is measured continuously. That's going to be normally distributed. In this question, according to a survey, 22.8% of credit card holding families in a certain area hardly ever pay off the balance. Suppose a random sample of 29 credit card holding families is taken. Find the probability that more than 3 families hardly ever pay off the balance. So this is not something we need a measurement tool for. We can just count the number of families. So more than 3 could be, it says more than 3. So that is 4 or more. So it could be 4 or 5 or 6 or 7 or 8. It can't be 6.5. It can't be 7.25. We're just counting here. And so that's what tells us that this is going to be a binomial distribution. All right, so it says probability that more than 3 families. So we're looking at 29. So the possible outcomes here, if you sample 29 credit card holding families and ask them, find out if they hardly ever pay off the balance, then there could be 0 that hardly ever pay off the balance. It could be 1, it could be 2, it could be 3, it could be 4, it could be 5, it could be 6, so forth and so on. It could be 28, it could be 29, and that's it, because we're only looking at 29 families. So somewhere between 0 and 29 of them hardly ever pay off the balance. What we're asked for here is to find the probability that more than 3. So more than 3 is 4 or more. Really important to recognize that. So in the normal distribution, more than 3 we can treat essentially as the same as 3 or more, because those are not the same, but they're infinitely close to being the same. Because in the normal distribution, the next thing larger than 3 is 3.0000, infinite number of zeros, and then a 1. And that is infinitely close to 3. But with the binomial distribution, if we say more than 3, the next thing bigger than 3 is 4. So we're looking for between 4 and 29 successes. Now, our calculator functions, neither of them find a number of successes or more. However, our calculator function can find the opposite. Our calculator function can always find a number of successes from 0 to some number, or that number or less is another way of putting that. So our calculator can find this. And what we know is that both of these two things added together, everything from 0 to 29, that's going to be 100%, or 1. So we're going to find the opposite of what we're looking for. We want 4 through 29. We don't want 0 through 3, but that's what our calculator can find. So our calculator can find that by finding the binom CDF. So CDF is the cumulative density function. That's the one that finds between 0 and some number. There are 29 successes, or there are 29 trials here. Probability of success, 22.8% is the number given in the problem, so 0.228. And then the number of successes we're looking for is 3 or less, so 3. Okay. All right. So, and this, again, is going to find us the probability that we have between 0 and 3 successes, which is not what we're looking for, but it'll help us find what we're looking for. So let's go ahead and find that. So let's see. So on our calculator, we go to distributions, and then we'll go up to binom CDF. Whoops, too far. All right. Number of trials, 29. Oops. 29. Probability of success, 0.228. and then x value, 3. All right. And so it's going to paste just this, and then we press enter, and we get 0.077 or 0.7660. 0.7660. All right. And wait, did I do that right? Yes. Okay. 0.7660. We usually going to do 4 decimal places, though, so I don't know why I wrote 5. 0.766. All right, so that is the opposite of what we're looking for. So to find what we are looking for, we're just going to subtract that from 1. So 1 minus 0.0766. So on our calculator, we can just do 1 minus that answer. And we'll get 0.9234, rounded to 4 decimal places. And so that is the probability that we're looking for. So anytime we are going in the greater than direction, we instead have to find what's in the less than direction, because that's what our calculator finds. The only reason we have to do this is because we're just kind of working around our calculator function. So what we wanted was 4 through 29. What we didn't want was 0 through 3. So we found 0 through 3 and then subtracted it from 100% to get our answer, which is now the probability of 4 or more, or in other words, more than 3. All right, let's look at another one. Actually, before we look at another one, one of the most common mistakes I see with the binomial distribution problems is some people just subtract everything from 1. They don't really know why they're subtracting from 1. They just go ahead and subtract everything from 1. That's a very bad idea. We only do that if we are going in the greater than direction. If this question had said, what's the probability that fewer than 3 hardly ever pay off the balance, then we wouldn't be subtracting anything from 1. So make sure you know when you're subtracting from 1 and when not to. Don't just memorize, always subtract from 1. All right, this one's another binomial distribution problem. In a certain state, 35.2% of all community college students belong to ethnic minorities. Find the probabilities of the following results in a random sample of 10 of the community college students. All right, so the thing to notice about this one is halfway through the question, or halfway through the 4 parts of this question, it switches what we're looking at. And so binomial distribution, the bi in binomial stands for 2. There are always 2 outcomes, and there's always 2 different ways to look at things. So anyway, all right. So first part, part A, exactly 3 belong to an ethnic minority. All right, so exactly is when we use the binom PDF function. And so that's going to be, we're looking at 10. We're looking for the probability that exactly 3 do belong. And so the probability that they belong, that's 35.2 or 0.352. And we want exactly 3. All right. So I'll let you calculate that out. I know you can plug that into your calculator, so we'll skip that step. All right, the next one, 3 or fewer belong to an ethnic minority. All right, so remember that the binom CDF function finds a number or fewer. So binom CDF finds with 10 as the number of trials, 0.352 is the number of successes, and then 3 as the number of successes. That's going to give us the correct answer there. So remember, binom CDF, this is going to find us between 0 and 3 successes. And that's not 0 minus 3, that is a range. 0 to 3 successes is what that finds. The binom PDF function, that's finding us exactly 3. All right, the next one, exactly 6 do not belong. Notice that we've switched now to do not belong instead of the probability that someone does belong. And so what this is going to change, this is going to change our probability. So our probability was 0.352. That's the probability of belonging to an ethnic minority. Now we want to look at the probability that someone is not in an ethnic minority. So we can figure that out by doing 1 minus 0.352. And that's going to be, let's see, 0.648. So that is the probability that someone does not belong to an ethnic minority. All right, so now that we know that, we can find these probabilities. So exactly 6 do not belong. So the exactly is going to be a binomial PDF. All right, so it's still 10 trials, but now probably they do not belong. That's 0.648. And then exactly 6, so that's 6 for the number of successes. And so that's going to find us exactly 6. All right, last one, probability 6 or more do not belong to an ethnic minority. All right, so again, we're looking at 10. So if we're looking at 10, that's going to be somewhere between 1 or 0 and 10. So there could be 0 people. That looks like a 6. 0. It's hard to write on a tablet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So 6 or more. That is these. 6, 7, 8, 9, 10. That is 6 or more. On these problems, I really recommend writing out the numbers like this. You don't necessarily have to write out all of them like on the last problem. I didn't write out all 30 numbers between 0 and 29, but I wrote out some of them. And it really, really helps to be able to visualize so that you can see what is it that we want, what is it that we don't want. All right, so here we want 6 or more. That is 6, 7, 8, 9, and 10. What we don't want is 0 through 5. But here's the thing. That's what our calculator can find. Our calculator can't find 6, 7, 8, 9, 10, but it can find 5 or less, which is the same as 0 through 5. So that's what we're going to find first. So we'll do binomial CDF, 10 trials. We're looking for the probability they don't belong, so that's 0.648. And then 5. So notice I am not using 6 here. That is typically what people do. The reason I am not using 6 is because we're about to subtract that from 1. And anything we subtract out is things we are removing. So that is, we took everything. The 1 here is everything. That's all of this. All of that is the 1. And we're subtracting out the part we don't want. We're subtracting out that, 0 through 5, which leaves us with only 6 through 10. That's what we wanted. If we had put a 6 here, then we would have been subtracting out 0 to 6, which would have left us with only 7, 8, 9, and 10. So when you are subtracting, the thing you are subtracting needs to be the things you want to remove, not including anything you want to keep. So be really, really careful of that. All right. Next question is another binomial distribution question. We won't work through this one, but it's very similar to the last one. So it says down a certain stretch of highway, the probability that a car will be speeding is 0.33. If the next 10 cars are observed, find the probability of the following. Exactly 8 are not speeding, so that's an exact one. That's going to be a binomial PDF. Less than 5 are speeding. So less than 5, we got to be careful of that because less than 5 really means 4 or fewer. So less than 5 means anywhere between 0 and 4. And then the next one, more than 2 cars are speeding. So more than 2 doesn't mean 2 or more. It means 3 or more. So that's 3 through 10. Those are the number of successes we're looking for there. So on A, we'll be using binomial PDF, and then B and C, binomial CDF. One of those we will need to subtract from one we won't. So I'll let you figure that out. If you're confused on which you do where, feel free to shoot me an email. All right, let's jump to game theory. All right. So on this next one, we've got research department at a manufacturing company has developed a new process that it believes will result in an improved product. Management must decide whether to go ahead and market the new product. The new product may or may not be better than the old one. If the new product is better and the company decides to market it, sales should increase by $50,000. All right, let's go ahead and start writing our matrix as we read the rest of the question. All right, so if they market the product, so that's going to be our first row. If they market the product and it's better, so let's make that our first column, then they are going to make an additional $50,000. So $50,000. All right, if it is not better, so not better is going to be our second column, and they replace the old product with the new product on the market, so that's if they market it, they will lose $24,000. So minus $24,000, because that's lose, right? If they lose money, it's negative. All right, if they decide not to market the new product, they will lose $50,000 if it's better. So our second row is going to be not market. If they decide not to market the new product, they'll lose $50,000 if it's better. So that's negative $50,000 if it's better. And they'll lose just the research costs of $20,000 if it's not. So that's negative $20,000. So that's our matrix. 50,000, negative 24,000, negative 50,000, negative 20,000. All right, if they decide to market the new, oh yeah, we already did that part. All right, so answers parts A through C below. Okay, so A was prepare a payoff matrix, which we just did. Parts B and C. So B is we're going to compute the expected values for both based on whether or not they think it's better. So let's say that they think the probability that it's better, let's just say that is 40%. Okay. That automatically tells us the probability that it's not better is 60%, right? Because one of those two things has to happen. So then to find our expected values here, all we have to do, this is just like Unit 2. It's just like the finance project when we're trying to find expected values. We got our X's and our P's. So marketing, if we market it and it's better, that's $50,000. And the probability that's better is 40%, 0.4. So 0.4 would be its P. And then not better, that's negative 24,000. And its probability is 0.6. So that's if they market. If they don't market the product, they lose $50,000 if it's better, and negative 20,000, so they lose 20,000 if it's worse. So both of those are negative. The probabilities are still the same. If it's better, that's 0.4, and then if it's not better, that's 0.6. All right, so then so this is not market. So then we just multiply down. So for the market one, we'd multiply 50,000 times 0.4, and then negative 24,000 times 0.6. Add those together. That would give us our expected value there. On the next one, negative 50,000 times 0.4 and negative 20,000 times 0.6. Add those together. That is going to give us the expected value there. Whichever of those values is higher is the one the company should use, because that means they have the best expected profit from that strategy, whether it's marketing it or not marketing it. So I'll leave you guys to actually calculate those expected values, but we've got it all set up so you can do it. I think part C is whether or not there are any dominated strategies. I can't remember whether it's dominated rows or dominated columns. Or no, maybe it's if there's a saddle point. I think that's what part C is. So saddle point, if you remember, we look for the smallest in each row. That would be negative 24,000 and negative 50,000. And then we look for the largest in each column. And so that would be 50,000 and negative 20,000. So nope, no saddle point here. So, all right, let's jump to the next one. All right, another game theory one. Allied Corp decides to launch its new product with a big television and radio advertising campaign. At the same time, Allied's major competitor, Bates Incorporated, has also decided to launch a big advertising campaign for a similar product. Payoff matrix shows the increased sales in millions for Allied, as well as the decreased sales for Bates. All right, so Allied is our row player. Bates is our column player. TV is strategy 1. Radio is strategy 2. Our matrix 2.5, negative 0.8, negative 0.1, and negative 0.1 shows that really Bates wins if anyone chooses radio, and Allied only wins if both Allied and Bates choose TV, because that value is positive. All right, so we're looking for our optimal strategies, and the first thing we always want to do when looking for optimal strategies is look for a saddle point. So saddle point, smallest in each row. First row, that would be negative 0.8. Second row, both the values are the same, so they're both the smallest. So we underline both of them. And then we will circle the largest in each column. First column, that's 2.5. Second column, the largest is negative 0.1. So turns out we have a saddle point. So we don't need to go through the long process of finding the expected values, finding our P1s and P2s, because there's a saddle point. We're done. Allied is going to choose radio, because that's where the saddle point is, 100% of the time. And they're going to choose TV 0% of the time. Because when there is a saddle point, both players always choose it. Bates, likewise, would choose TV 0% of the time and radio 100% of the time, again, because that is where the saddle point is. So, optimum strategy for Allied, 0 and 1. They're not going to choose TV. They're going to put 100% into radio. And then the value of the game, well, that's just the saddle point itself, negative 0.1. That's it. All right. Next one. In the game of matching coins, each of two players flip a coin. If both coins match, that's both show heads or both show tails, player A wins $1. So we've got a matrix set up here where heads is option 1, tails is option 2. So if they both match, both heads or tails, player A wins $1. So that's 1 in the top left and 1 in the bottom right of our matrix. If there's no match, player B wins $1, so that's going to be negative 1 in both of those spots, the top right and the bottom left. All right, so there's our payoff matrix. So then we want to find the optimum strategy for player A, the optimum strategy for player B, and the value of the game. All right, so this problem, finding the optimal strategies. So one, we should always check to make sure there's no saddle point. So we can do that. Smallest in each row is the negative 1. Largest in each column, those are the positive ones. So no saddle point here. Now that we know there's not a saddle point, every single example like this is exactly the same. So if you're having trouble with one of these examples, it's not because of the example. It means you don't quite understand the process. Because every single one of them is the same. There is no difference in any one of these problems once we figure out there's not a saddle point. So if you're having trouble with one of these, we'll work this one out, but go back and watch one of my example videos where I work an example. Just watch it. Have your example and have that example, and when I do something in the example video, if I take the top left element and I do something with it, do the same with your example, with whatever your top left element is. Just do it step by step, because it is always going to be the same every single time, I promise. All right, so this one. All right, so we want to find the optimal strategies for A and B, and we want to find the value of the game. All right, so first thing we need to do is find the optimal strategies for player A that is based on what player B does. So first thing we do is we look at what happens if player B plays a heads or flips a coin and chose heads. So those values are 1 and negative 1. All right, so set up our expected value table with 1 and negative 1. We'll let heads be P1 and tails be 1 minus P1. All right, so then we'll multiply down, so that's 1P1, and then we'll go ahead and distribute the negative 1 times both of these two things. So negative 1 times 1 is negative 1. Negative 1 times negative P1, that's going to be a positive P1. So that's going to give us 2P1 minus 1. All right, so that's our expected value for A, given B chooses heads. All right, and then we're going to do same thing, expected value for A, but now if B chooses tails. All right, so expected value table is now negative 1 and 1. and then P1, 1 minus P1. All right, so we'll multiply down. That's negative P1, and then plus, we'll distribute the 1. 1 times 1 is 1. 1 times negative P1, negative P1. All right, so that's going to give us negative 2P1 plus 1. All right, then we're going to set those equal, because what we want to do here is we want to remove the other player from the game. We want the expected value if B chooses heads to be the exact same as the expected value if B chooses tails. That way we know what the expected value is no matter what the other player does. So we'll set these equal to each other, add 2P1 to both sides. That's going to give us 4P1 on the left there. Add 1 to both sides. That's going to give us 2 on the right. And that's going to give us, and then divide by 4. That's going to give us P1 equals 2/4 or 1/2. So A is going to play their first strategy, heads, 1/2 of the time, which also tells us they're going to play tails 1/2 of the time as well. All right, so that is the optimum strategy for player A. Next, we want to find the optimum strategy for player B. Now, because our matrix is symmetrical, it's going to end up being the exact same, because our expected values for B are going to be X and P, X and P. We'll do the 2 rows. So that is expected values for B are based on what A does. So if A flips the coin and it shows heads, that's 1 and negative 1. P2, 1 minus P2. And then if expected value for player B, if A flips a tails, that's negative 1, 1, P2, 1 minus P2. And you'll notice those are the exact same 2 values in the X values as we had for player A. So we're going to end up with the exact same thing. We're going to end up with 2P2 minus 1 equals negative 2P2 plus 1, which is going to give us that P2 equals 1/2. So optimum strategy for B, choose heads half the time, and that of course means tails half the time as well. All right, and then the value of the game, we'll multiply those matrices together. So that is A's optimal strategy, 1/2, 1/2. That's a 1/2 matrix. The payoff matrix, 1, negative 1, negative 1, 1. And then times B's optimal strategies, 2/1 matrix, 1/2, 1/2. And that's going to give us the value of the game, which is going to be $0. So that's how we can find that. We can also find the value of the game by plugging P1 into either of the P1 expected values, or by plugging P2 into either of the P2 expected values. We'll get 0 there as well. All right, so that's how you do that. Like I said, it's going to work the exact same every time. This case, we ended up with the same values for P1 and P2. That won't happen every time, but we do the same process. We find the expected value for A if B picks option 1. We find the expected value for A if B picks option 2. We set those equal to each other and solve for P1. Then we find the expected values for B if A picks the first option, and then the expected value for B if A picks the second option, and that helps us find P2. And then we find the value of the game, and that's it every single time. All right, the last one we'll look at is another one. This is the one that I've gotten the most questions on. So the number of cases of African flu has reached epidemic levels. The disease is known to have 2 strains with similar symptoms. Dr. Godecker has 2 medicines available. The first is 73% effective against the first strain, 42% effective against the second strain. All right, so that means our answer is either C or D here, because first row of our matrix should be 0.73 and 0.42. And then let's see, the second medicine is completely effective against the second strain, so that should be a 1 in the second column, but ineffective against the first, so that should be a 0 in the first column. So D is our correct answer here. Our matrix should be 0.73, 0.42, 0, and 1. Once we figure that out, it's the exact same process as before. We're going to set up our expected values. We're going to find our optimal strategies. Exact same thing as before. The only difference in this problem is it doesn't ask you for the optimal strategy for the strain of the flu. It only asks you for the optimal strategies for the doctor, which is the row player. But that's okay. You don't have to be asked to do both parts. The last part, the effectiveness in prescribing the medicines in this way, that's the value of the game. So again, this example is not any different than any of the others. So start off by finding the optimal strategies for the doctor by looking first at what happens if it's strain 1. So that's going to be 0.73 and 0. And then find the expected value if it's strain 2. That's 0.42 and 1 as those x values. Have P1 and 1 minus P1 as your probabilities. Solve those, set them equal. That's going to give you this value right here, the probability with which the doctor should use the first medicine, and then subtract that from 1 to find the probability with which the doctor should choose the second medicine. So again, all of those examples are the exact same. If you're having trouble, watch one of the example videos or rewind to when we did the coin flipping example because they'll all work the same. All right. That's it for now. Good luck on your test.